Hey, this is Mr. Drogemeyer. Thanks for joining me for our Unit 3 test review for Algebra 1. Today we're going to be looking at some problem examples that will be very similar to what you're going to see on your unit test. So let's go ahead and jump in and get started. Our first question here asks us to determine which property of equality we would be using to isolate the variable in these different linear equations. And so we talked about addition property of equality, subtraction property of equality, basically saying that if we add something to one side of an equation, then we also need to add it to the other side to maintain that balance or that equality in the equation. So in this first example, when I have x plus 6 equals 8, if I'm solving for x, I want to isolate that variable, then I need to undo that addition that's being done to the x right now. And so to do that, I have to subtract 6 from each side. So that's using that subtraction property of equality. In the second one, I have x minus 7 equals 5. I would want to undo that subtraction. So to do that, I would have to add 7 to each side. So I would be using that addition property of equality. Now this one's a little bit trickier here. I have x minus 12 equals 2x. Couple of ways that I could think of this. I would need to get the x, x is on one side to isolate that variable, and I would need to get the constant on the other side. And so in doing that, in isolating the variable, though, we need to move that minus 12. And so when I do that, I'm adding the 12 to each side. So I'm really using that addition property of equality with the constant. In solving, then I would need to move this 2x over and so on. But we're talking about isolating the variable. Our first step here would be to move that. And then in this other one, x plus 15 equals 3x. Again, I want to undo that addition by 15. So I'm going to subtract the 15, so subtraction property. All right, in our next one here, we're going to be using the same idea here. Oh, excuse me. First, this one says if rain is falling at 0.25 inches per hour and 1.75 inches have already accumulated, how many hours must have passed if there are 3 inches of rain? We want to create a linear equation that's a model for the rain that's accumulated. So this is a rate of change problem, and we talked about in the unit problems like this when we're creating those equations. It's going to look something like this. We're going to have the rate times the variable plus the initial quantity, and that's going to equal the specific quantity that we're trying to find, or that we're trying to get to. And so in this problem that they've given us, we have a rate. It's falling at 0.25 inches per hour. We want to know how many hours, and so our variable is going to be h, and so that rate is the 0.25 times the number of hours. Initial quantity, well, we had a 1.75 inches that had already accumulated, and then the specific quantity, we want to know how many hours it's going to take for us to get to 3 inches of rain. And so that's how we would go about creating that equation. And the order here doesn't matter. I could have started with the initial quantity since it's just addition there. Either one of those ways of showing that equation is correct. All right, then in number 3, given the linear equation 5x plus 2 equals 9, they want us to identify the variable, the constant, and the coefficient. Well, our variable is going to be our unknown quantity. So our variable is going to be x in this case. As far as a constant, we actually have two constants here. Constants are going to be our numbers that are not being multiplied by a variable. So 2 and 9 would be considered constants in this equation. And then coefficient is going to be any number that's being multiplied by the variable. So we have 5 here would be our coefficient. All right, problem 4. Which of the following equations here has a variable that's equal to 4? So we want to solve these equations for x, and we want to see if any of them have x equal to 4 to make that equation true. So with our first one here, 2x plus 6, I would start by isolating the variable. So I'm going to subtract that 6 from each side. And I'm going to write this up here. So I'd have 2x is equal to 14 minus 6 is 8. And now x is being multiplied by 2. So I would need to undo that multiplication by dividing. 2x divided by 2 is x, and 8 divided by 2 then is 4. So A would be one equation that has x equals 4. In our second equation here, that 6x, we're adding 8 to it. We would want to subtract 8, undo that addition to isolate our variable. Would leave me with 6x equals 26 minus 8 is 18. And then we'd undo that multiplication by dividing. 6x divided by 6 is x, 18 divided by 6 is 3. So that second equation does not have x equal to 4. Third equation, we would start by subtracting 8 to isolate that variable, which gives us 8x equals 24 minus 8 is 16. And then we'd undo that multiplication by dividing, and we get that x equals 16 divided by 8, which is 2. So that one is not one of our correct answers. And then our last one here, we're adding 4 to the 7x, so we need to subtract 4 for our first step. That leaves us with 7x equals 32 minus 4 is 28. And then we undo that multiplication by dividing by 7, and x equals 4 in this case. So A and D would be our two equations where the variable is equal to 4. All right, next problem. We have this equation 15t plus 25 equals 100. They want to know what would our first step be in solving that equation for the variable t. So we have 15t plus 25 equals 100. We want to isolate that variable t. And so our first step is going to be we have an addition happening here. We also have a multiplication. You can kind of think of it as the reverse order of our order of operations. We're undoing things. So we're going, so the last thing we always do in order of operations is addition and subtraction. And so if we're undoing, we're going to undo the last thing that was done. So we're going to undo that addition. So our first step here would be to subtract 25 from each side. All right, and they didn't ask us to solve for t, they just wanted to know what our first step was there, and that would be it. All right, next one, number 6. In this one, they want to know whether the units that they've given are commensurable or incommensurable with meters. So when we talked about this vocabulary term, commensurable meant that the units that we're talking about are measuring the same type of thing. So in this case, we're talking about meters. Meters measures distance. And so if units are going to be commensurable with meters, they're also going to be measuring distance. Incommensurable means that they're not measuring the same type of thing. So, excuse me, in our examples here, so meters is distance, kilograms is going to be measuring a weight. And so that's going to be an incommensurable measure. Miles, that is a distance, and so that would be commensurable with meters. We could convert between meters and miles. Hours is measuring time. That's going to be different than distance, so that's incommensurable. And then centimeters is another measure of distance. That would be a commensurable measure. All right, number 7, same idea here. This time we're talking about grams. Grams is measuring a weight. And so acres is going to be measuring distance or really an area. Um, and so that's going to be an incommensurable measure. Yards, we're talking about distance again, that's incommensurable. Pounds is a weight, and so grams and pounds would be commensurable. Grams and kilograms would also be commensurable. They're both measures of weight. All right, in number 8, it says in an election, a candidate will win if they receive 104,453.74 votes. And so would the candidate need 1,453 votes or 104,454 votes to win? So we want to think about, they probably did some kind of an average to come up with this number that is needed to win, but it's not actually possible for them to receive a decimal, a fraction of a vote. So which one would they need to have to actually win? Well, they would need to get the larger number, the 454, because this one would be less than the amount needed to win. So even though they both have 104, 453 in them, that extra decimal on there, that's adding to the number that they need. So we would need to go thinking about rounding. We would be rounding up there. They need to get to 454 to actually have enough to be declared the winner. All right, in number 9, asking what are some valid rearrangements of this equation or this formula. So to find a Fahrenheit temperature, when we know the Celsius, we take 9/5 times the Celsius measure and add 32. Well, when we talked about some of these things, we said we could rearrange them to solve for a different variable. So we could try to isolate the C, since right now we have F isolated, and to isolate C, I would start by subtracting 32 from each side, right? Because right now I'm adding 32 to that 9/5 C, and if I do that, I get F minus 32 equals 9/5 C. So that's one way I could rearrange it. I could go further and completely isolate C. And to do that, right now it's being multiplied by 9/5. So I would need to undo that multiplication. Well, undoing multiplication is division. If I'm dividing by a fraction, it's the same as multiplying by its reciprocal. So to do that, I would multiply each side by 5/9. Reciprocal just means we're flipping that fraction. And so on each side of that equation, I would be multiplying by 5/9. And so on this side, I would have 5/9 times the F minus 32. And on the right side, the 9/5 times the 5/9 equals 1. So that's just 1C for C. So these would be two possible ways that we could rearrange that, that particular equation. All right, in number 10, it says given that V equals 90 volts of an outlet in a select country and I equals 0.5 amps that are being pulled to that 90-watt bulb, we want to solve this equation V equals I times R in terms of R, and then we want to substitute in those given quantities. Well, so solving this equation for R means we want to isolate that R. Right now it's being multiplied by I, so I would start by dividing each side by I. And when I do that, Here I get v divided by I. On this side, I just have r. So there's my equation solved for r. Now we're going to substitute in the values that they gave us. So r is equal to v, which is 90, divided by I, which is 0.5. And we're going to go ahead and do that division. If I take 90 and I divide it by 0.5, I would get 180. And then we also want to think about, or excuse me, so R here, which is our, that's the wattage that's being pulled from that bulb. So 180 would be our solution here. All right, number 11, asking about which of these would be valid rearrangements of the formula that they gave us here. So P equals 1/2 times A plus B times H. And so if we look at this first example, we have the A plus B. So we want to look at what happens. How would I isolate that A plus B? So I'm going to do some work down here. So I have my original equation. And so right now, the A plus B is being multiplied by 1/2 and by H. The way they write this, they remember this is all multiplication, so I could have the H over here. It wouldn't change what we're doing. So I would need to undo that multiplication, I would need to divide by 1/2 and by H. Well, dividing by 1/2 is the same as multiplying by 2. So let's start with that. We're going to multiply each side by 2, which would give me 2p equals A plus B times H. And then I would need to divide this side by H to undo that multiplication. And so I would have A plus B on this side and the 2p divided by H on this side. And so that first example they gave us, that would be a valid rearrangement of that particular equation. All right, the second one, so they have rewritten this as P equals 1/2 times AH plus BH. Well, it looks like they've distributed. And so I'm going to rewrite it this way just because it's a little bit easier to look at it this way. So this 1/2 times H, if I distribute that, I would need to multiply it by each term that's inside of the parentheses. So that would be 1/2 HA or AH. And then I would also have 1/2 BH. And so this one would be invalid because they did distribute the H, but they only distributed the 1/2 to that first term. It would also need to be distributed to that second term. So that's the mistake or the problem with that one. All right, in our next one here, they have solved it for H. And so let's, and again, I'm going to put the H there. It just helps me to see it a little bit better here. All right, so I would start by dividing each side by 1/2, which we said is the same as multiplying each side by 2. So if I multiply this side by 2, I get 2p. If I multiply this side by 2, I have h times the a plus b. Now I would need to solve for h, I would want to divide by that whole quantity there, a plus b. And when I do that, I'm left with just h here, and on this side I have 2p divided by a plus b. And so this one is invalid as well. They have that fraction flipped. It should be the other way. It should be the 2p in the numerator, the a plus b in the denominator. All right, and then our last one here, it's kind of a long problem. I appreciate you hanging with me here. What happens, or they have it solved for p, but they just have 2p there. So if we think about, if I just have a plus b times h over here, then that means they got rid of the 1/2. So they divided each side by 1/2, or like we said, multiplied each side by 2. Over here, that's 2p. Over here, that would be a plus b times h. And so that would be a valid rearrangement of that particular formula. All right, let's move on then to number 12. And in this one, they've just given us some different objects and asked us which of those measures would be best to use. Would it be better to use kilometers or to use meters? Well, if we measure the distance from Wichita to Kansas City, that's going to be a very large distance, kilometers. If we think of, in terms of standard units, we measure in miles when we're talking about those long distances. Kilometers is going to be similar to miles there. All right, my height. So when we measure height, we're using feet and inches. Metric system, we're going to use meters. That's going to be kilometers is going to be too large of a measure to use. Meters is going to be the one that would be best here. A marathon, when we're measuring long distance running, again, a long distance, kilometers is going to be what we're looking at there. And then the height of a tree, kilometers, that's going to be too much, too large of a measure. Meters would be a better unit there. So just thinking about reasonable units of measure for those. All right, and number 13 says, in your own words, explain why solving this equation 4 equals x divided by 3 uses the multiplication property of equality. And then we want to provide an example with our answer. So we want to explain how we go about solving it. So right now we have 4 equals x divided by 3. So we would want to say that we use that multiplication property of equality to solve it, because we're isolating that variable, and to isolate the variable we need to undo the operation that's being done to it right now. So right now x is being divided by 3, and so to undo that operation we would need to multiply each side of the equation by 3. So in answering this, we would want to explain how we solve it. So just like we've done there, and then it says to provide an example, showing how you solve it. That tells me the example that you're looking, or that we're looking for there, why we're using that multiplication property. All right, next one here says a school needs to buy new tablets for 6 classrooms. If the school needs to buy 16 new tablets in each classroom, how many tablets does it need to buy in total, and explain. So this would be a case of us needing to multiply, because we need 6 in each classroom, or 16 in each classroom. We have 6 classrooms, and so we need to multiply those together to figure out how many we need to buy in total. And really that would be just explaining that since we need a certain amount in each one, we're going to multiply that quantity times the number of rooms to figure out how many we would need to buy in total. All right, the next one here, explain why days, grams, and centimeters are not the appropriate units for measuring the distance from your home to the grocery store. All right, and mention a realistic unit that we could use for this measurement. So we would just want to talk about, what do these measurements, or these units measure? So days is a measure of time, grams is a measure of weight, centimeters is a measure of distance. But when we're talking about going from place to place, a home to a grocery store, that's going to be a pretty large distance in most cases, and so centimeters isn't going to be your best unit of measure for that. So using something like kilometers or miles would be a much better, much more realistic unit of measure in that case. All right, and then I believe that is our last one, and it is. All right, well, that's all I've got for you for our unit test review. Appreciate you taking the time to watch. As always, if you do have questions, please let me know. Thanks. Have a great day.